A subsea pipeline isn't just a simple tube carrying fluid from point A to point B. It's actually under attack from really three directions at once. Today, in this explainer, we're diving into the hidden complexities of subsea pipelines and the incredible structural engineering required to keep that steel intact deep underwater. Okay, let's dive right into this. These pipelines, they are highly engineered structures fighting a grueling three-front war. Every single day of their operational life, they are under attack from three distinct directions, literally all at the exact same time. So what does this battlefield actually look like? Well, first, you've got internal pressure from the produced fluid, relentlessly pushing outward against the pipe wall. Then, you've got external hydrostatic pressure from the crushing weight of the ocean, pushing inward. And third, and this is absolutely huge when we talk about high pressure, high temperature, or HP/HT service, the pipe is fighting to expand lengthwise from the intense heat of the fluid. But because the seabed holds it in place, that thermal expansion becomes a massive physical issue. Getting the wall thickness right means you have to account for all three of these extreme forces simultaneously. Which brings us to the ultimate engineering balancing act, the wall thickness dilemma. Think about it. If you design a wall that's too thin, it bursts. Game over. But if you make it needlessly thick just to play it safe, you waste an enormous amount of steel. And remember, we're talking about a macro to micro problem here. A few extra unnecessary millimeters of steel multiplied across a route that runs for miles and miles, that will absolutely wreck a project's economics. Precision here is an absolute necessity. To get that precision, we've got to dismantle a common myth. There's this dangerous assumption that pipeline design is just a simple pressure calculation based on a thin wall model. In a basic thin wall assumption, we just pretend the stress is totally uniform all the way through the metal. But the thick wall reality of deepwater physics? Totally different story. When you get into serious HP/HT flow lines, the stress is absolutely not uniform. Enter our hero solution, the Lame hoop stress equations. These are the advanced formulas you strictly need for thick-walled HP/HT flowline design. Unlike the simple equations, the Lame equations actually account for the non-uniform circumferential stress distribution across the pipe's wall thickness. It calculates stress as a function of the internal and external pressures, plus the pipe's inner and outer radii, giving us the real technical vocabulary needed to grasp the physics here. Now, what's really interesting here is the stark difference between the inner and outer wall. Think of the pipe wall kind of like the rubber of a balloon under pressure. For a simple, thin balloon, the stress is pretty uniform. But for a subsea pipe wall thick enough to matter structurally, the stress acts completely unevenly. It hits the inner radius, the surface closest to the high-pressure fluid, much, much harder than the outer radius. The stress is incredibly concentrated right there on the inside. And this leads us right into a massive trap that catches a lot of junior engineers. So let me ask you, is a simplified thin wall calculation always conservative for genuinely thick-walled HP/HT pipe? Like if you just use the simple math, does it always err on the safe side? The answer is a definitive no. Way no. Using a thin wall formula on a genuinely thick-walled line is actually unconservative. Because the simple formula assumes the stress is spread evenly across the steel, it severely underestimates that peak inner wall stress we just talked about. Assuming the simple formula is safer can actually leave your pipeline dangerously underspecified for real-world operating conditions. Just to emphasize how severe this is, listen to this direct warning from our source material. Quote, applying thin wall stress formulas to a genuinely thick-walled HP/HT pipeline underestimates peak stress at the inner wall, a design error, end quote. So a design that easily passes a simplified check might actually be structurally unsound when subjected to real high-pressure, high-temperature service. It is a critical mistake. So how do you know when to switch up your math? Well, it all comes down to the number 30. This is the critical diameter to thickness ratio, or D/T threshold. If your pipe's D/T ratio is greater than 30, you're generally fine with thin wall math. But the second that ratio drops below 30, your pipe has officially crossed into dangerous thick wall territory. That is exactly when the simple math fails, and the Lame equations become absolutely mandatory. This brilliantly illustrates a core principle of engineering physics. It's kind of like the weightless rope analogy. You know, in high school physics, you often assume a rope is weightless just to make the math easier. And that simplification works perfectly fine, right up until the real-world mass of the rope becomes too massive to ignore, fundamentally changing your answer. HP/HT pipelines are exactly the case where the wall's thickness becomes so significant that simplifications just go out the window. Because engineers aren't just designing for an average, sunny operating day. No way. We're designing for the absolute worst-case scenario. The wall thickness has to be engineered to survive the exact moment when maximum internal pressure, minimum external hydrostatic support, and peak thermally induced axial compression all strike the pipeline simultaneously. That's the true survival condition the pipe has to be built for. Okay, let's zoom back out to the macro level for a moment to see how all this connects to the broader subsea system. Remember a previous explainer where we compared manifolds to plets? We learned that while a manifold acts like a highway interchange to commingle flow for multiple wells, a plet, or pipeline end termination, acts as a massive structural anchor holding the end of the line. So the crucial point here is that pipeline wall design and plet foundation design are permanently linked. You have to solve them together as one giant puzzle. See, because the hot fluid heats the pipe, the steel naturally wants to expand, but the seabed friction restrains it. So that expansion energy has nowhere to go and literally converts into immense axial compressive stress inside the pipe wall. And that exact same thermally generated force is what pushes so aggressively against the plet anchors at the ends of the line. The plet foundation has to be massive enough to absorb that axial force without shifting even a little bit. Otherwise, the jumper connections at the ends could be pulled right out of tolerance, creating a dangerous leak path. Let's summarize how this builds into our core takeaway for today. If you're dealing with a standard pipeline where the diameter to thickness ratio is greater than 30, you can confidently use your simplified thin wall calculations. Easy enough. But the moment you enter the realm of HP/HT thick-walled pipeline design, you've got to abandon those assumptions entirely. You have to use the Lemay hoop stress equations to capture that critical, non-uniform inner wall stress. We've seen how thick these walls can get, meaning these pipelines and their connected plats become incredibly heavy. We are talking tens of millimeters thick for high-pressure service. Which leaves us with one final provocative question. How do we safely lower these massively heavy, highly engineered structures thousands of feet through the ocean to the seabed without breaking them under their own weight during installation? Well, that dynamic challenge is exactly what we'll uncover in our next explainer. See you then.